My thesis project was titled Fast Transients from Magnetic Disks Around Non-Spinning Collapsar Black Holes, or basically how to blow up a star with a disk. I was advised by Dr. Orr Gottlieb here at the Center of Computational Astrophysics, who is also now moving on to MIT. So we've kind of gone over this with some of the other people, but the life cycle of a star, we start out as a molecular cloud of dust, and an average star would be like our sun. So anything less than 8 times the mass of our sun is considered average. When they reach the end of their life cycle, they'll puff up to a red giant, they'll slough off that material, become a nebula, and you'll end up with a compact core of the material becoming a white dwarf. However, if you're a massive star, anything above 8 solar masses, you become very creative, a red supergiant. And these objects will go supernova, and will become either a neutron star or a black hole, depending on the mass of the core when it goes supernova. So collapsars and GRBs, these are the things that I was focusing on. So gamma ray bursts are these jets that are coming out of the material, and a collapsar is when a star collapses directly into a black hole. So when massive stars exhaust their fuel, gravity overcomes the pressure, causing the star to collapse. And rapidly spinning black hole forms and power a GRB. So as the accretion disk forms around the black hole and the magnetic field lines that were originally streaming through the stellar envelope of the star is now being accreted onto the black hole. The black hole is spinning near the speed of light, and the rotation of the black hole causes these magnetic field lines to rotate around the black hole, and it creates essentially a particle accelerator. And a fire hose of material is launched as this material falls onto the black hole, is launched in both up and downwards from the black hole along the axis of rotation. This material is launched at nearly the speed of light, and when these supernovas happen, they briefly outshine the host galaxy that they occur in. So what powers the jet? So as I was saying, this is called the Blandford-Zanaik process, and essentially, as I was saying, as those magnetic field lines are accreted onto the black hole and the black hole is rapidly spinning, these magnetic field lines rotate around and will reconnect and will actually act as a particle accelerator and extract rotational energy from the black hole to launch this material out. So we know a lot about when black holes are moving at the speed of light, we get our gamma ray bursts. And we know a decent amount about what we call normal supernova, or just spherical collapse, generic supernova. But what happens in between when the black hole is rotating or some sub-relativistic outflow? We don't know. So that's where my model comes in. So I ran 3D GRH MHD simulations of collapsars with So we start with a 14 solar mass stellar envelope that collapses into a 4 solar mass black hole. We used Wolf-Rayet stars, or rapidly rotating stars. So the stellar envelope is much thinner than would be in a typical star this mass. This rapid rotation causes an accretion disk to form almost immediately after collapse. The magnetic field lines from the star get accreted into that into the disk, and we have a magnetic field strength 10 to the 12.5 Gauss, which is approximately the strength of a neutron star. Insane, like hundreds of thousands or millions of times stronger than the magnetic field of the sun. And so what happens if the black hole's not rotating? Do we still get a jet, even if there's, you're not extracting the material from the black hole, or you're not extracting the rotational energy from the black hole? So here we'll see a full 3D simulation. So this is 23 seconds from the point of collapse. At zero seconds, the black hole forms, and you'll see what happens. So you can't see the total star. This is the very innermost radius, so it'll span out, and you'll see the different colors of density shells. So even without any rotation in the black hole, there is still these massive outflows that we're getting. Now, they aren't as collimated as you would normally see in a GRIB jet. These are much wider. They aren't moving nearly at the speed of light. They're about half as speed. But they are still launching enough material, and now we're getting to the stellar envelope, and you get this large double lobe structure in the star. Now, the simulation's rotating. It's not actually spinning, but just so that you can get the full projection. So here what you see is the outer bubbles of the star. So this is the thinnest material, and as it gets thicker as it goes in. Now, the material that is in red is where there is presence of strong magnetic fields. So this is completely magnetic flux that is forcing this material out. And then here is the magnetic flux of the star at the very last moment of my simulation. So the black dot or the white dots represent the original radius of the star. And so what you see is these outflows are blowing out way beyond the star, and you get these huge double lobe structure. So what is it? So what is powering these outflows? Oh wait. Okay, never mind. We'll go to that in a minute. So let's talk about the efficiency of these outflows. So this is a theoretical model by Lowell et al. 2023 that shows the theoretical power of the BZ jet, the Blanford-Zneit jet, as a function of the spin of a black hole. 1 being the speed of light, 0 being nothing. So these are the outputs of my simulation, different parameters that I run, with the main versions of my simulation, and then the one you just saw is the X. And what we see is we are getting way more efficiency out of these outflows than is expected. So what is powering this increase in efficiency of material from the material? So one possible explanation is this Blanford Pain mechanism. So it's a similar mechanism, but instead of rotating around the black hole, you actually get these little vortices in the disk itself. And this causes a similar outflow, but these aren't nearly as powerful or relativistic as the BZ jets. So the other thing we see in our simulations are what we call magnetic flux eruptions. So you'll see this is XZ density, XY density, so looking top down from the disk, and then this is sigma, so this is magnetic flux. And what we see is we have these outflows in the disk itself that, we have a complete void here, and it's from a buildup of magnetic flux. And we see it again here. We have this large cavity here, and then we have a few here. And what we see, sorry for the quality of these GIFs, but what you see is where these outflows are coordinate with where the magnetic flux buildup is. And what you actually see is there's in this one specifically, you see a buildup of magnetic flux and it bursts out. And you can actually see that happen here. As the flux bursts out, you get the outflows. So what would this look like if you were to actually see this? So this is a magnitude plot which shows how bright an object would be seen through one of our telescopes. And what we use here is the filter bands for the new LSST telescope that just launched, as well as the Ultrasat near UV that will be launched soon. And then these are the cutoffs of what is visible within those detectors, the dotted lines that go across. So what we see is this object will be visible in all of these bands. So this will be a visible object within the sky. And for reference, the sun would be about -5. So this is, huge orders of magnitude brighter than what the sun would be. So in summary, there is a huge gap in our knowledge of subrelativistic core collapse supernova. We know a lot about relativistic and non-relativistic, but this subrelativistic category where the material is moving at a fraction of the speed of light. These hybrid outflows, the Blanford Pain and these magnetic flux eruptions, are present and dominate in models up to a spin of 0.4 the Black speed of light, and that the cooling emission from these from this explosion is observable in all filter bands of LSFT up to 200 megaparsecs away. And that's it. Any questions?
Thanks for that exploration of your work, Justin. That was great. Could you explain a little bit more what you mean when you were talking about the possible energy being produced through the Blandford-Payne mechanism? I didn't quite understand, because it seemed like most of the energy was in this sort of like giant outflows, which doesn't quite match the Blandford-Payne. So
okay, so what you see is this general central outflow. Now, there is no rotation in the black hole. So, though it may, we call this Blandford-Payne outflow because it is the rotation of the magnetic flux vortex is caused by the disk. Because the black hole is not rotating, you have this magnetic flux still accreting onto the black hole. Black hole's not spinning, but the disk is spinning very rapidly. So you get a very similar mechanism, but it's not nearly as powerful because you're not extracting energy. You're extracting rotational energy from the disk, not from the black hole. And then we separate these from what we call magnetic flux eruptions, because these are when that buildup of flux gets too high and it shoots these out from the black hole. They're not forming by themselves as in random areas of the disk. They are always shooting from the black hole. Anna?
Great talk. So out of like all the supernova we could possibly observe, how many are expected to like look like this, like have some rotation when the black hole is formed? Do you have like a percentage or fraction?
It's definitely in my paper, but off the top of my head, I do know that most even the GRB fraction is very low of total supernovas that we see, and this I imagine would be this could be an order higher or an order lower depending on how prominent these objects are. And the problem is there's so many. There's very vast. There's low luminosity GRBs. There's fast blue optical transients. Just a lot of categories of objects that we don't know how they form, and we're trying to find possible mechanisms to form those objects. So we may have already observed something like this happening, but we just don't know because we have no classification for it. So, anyone else? James?
Yeah, thanks, Justin. I guess I'm still a little unclear on the relationship between the spin rate of the black hole and the type of outflows that we see. Like you mentioned that there are relativistic outflows and there are non-relativistic outflows, and then you're looking at sub-relativistic outflows, but looking at very low spins. Mm-hmm. So what types of spins would we expect for non-relativistic outflows, and what would be the reason for the difference between those outflows and these sort of sub-relativistic outflows?
So it's hard to tell because having a non-spinning black hole is almost a non-physical thing that is possible. So we just wanted to cut that power completely out of the scenario. And so what our argument is that these outflows are present all the way through here. But it is at some point around 0.2 to 0.4 spin the black rotation of the black hole that you get where the central outflow dominates over the outer outflows. So that's what you end up seeing is the central GRB. But even still, most relativistic outflows are coming from black holes that are spinning 0.8 to 0.9 to 1. You know, we're reaching maximal spinning black holes to get these relativistic outflows. A lot of times in here, if you don't have enough magnetic field strength, not enough rotation, you end up with failed supernovas, or something along those lines. So it's one of those things where everything accounts for something, so it's hard to categorize it so tightly. But any other questions? Okay, thank you.